Let's speak about strings. So strings are, of course, sequence of characters. We refer to characters usually as an alphabet. An alphabet is just a finite set which contains all the characters of interest. Natural examples include things like binary strings, or all the ABCD, or ASCII, right? 8 bits encoding most of the letter and characters and so on that you can type in 8 bits. Or you can do more exuberant things like having UTF-8 and so on. But alphabet can also be just direct command: move ahead left, move ahead right, jump, etc., etc. Okay, so formal definition of a string is that it's a sequence, a finite sequence of character from an alphabet. An important string would be the epsilon, which is just the empty string. It's a string of length 0. The length of a string is, of course, just the number of characters in the string. And I should mention, by the way, that usually we'll use capital sigma as the notation for the alphabet. That would be the set of characters we can use. And in particular, sigma to the n would be all the string of length, exactly n characters. And an entity that would be very important for us is sigma star, which is going to be the collection of all possible strings, right? So it's going to be, you go from length 0 to infinity of sigma to the I. Sigma to the I. Okay. Okay, and you can define a string recursively or inductively, and this kind of a weird definition is convenient when trying to prove formal things about strings. So a string is either epsilon, the empty string, and it has length 0. And alternatively, if it's not empty, then a string is defined recursively as a leading character A, right? Followed by a string x, right? And the length of the string in this case is 1 plus the length of x, right? So this is a bit bizarre, so maybe I should give an example. So Sariel, the definition of the string Sariel is in this recursive form would be this s, this would be a in the above thing, and this would be the x, right? Or maybe let me use s, right? So the string Sariel is made out of first character s and then a string x, which is what remains. And of course, you can define, instead of defining it as the first character, you can look on the last character. So in this case, Sariel would become, right, x and s. And this would be, L, of course. I should know my own name, right? You would hope. And x would be Sari, and L would be the suffix. Okay, so, and the length again is 1 plus the length of the suffix. Okay, now we're going to have a convention that characters in the alphabet we will use small English letters. String we will usually use W, X, Y, Z characters for strings, and set would be capital letters. Okay, now this stuff is very confusing, and students get very confused by this concept of empty string. So epsilon is the empty string. It's just a string of length 0, right? Now, this, on the other hand, is a set that contains a single element, and this single element is the empty string, okay? Now, this is to be distinguished from this, right, phi, which is just a shorthand for this, which is just the empty string. right? So empty set, sorry, not empty string. So this is the empty set, and in particular, notice that this, oops, let me try again. This is different than this, right? So what I wrote on the left is the set that contains a single element, and this single element is the empty set, while what I wrote on the right is an empty set, right? So the set on the left has one element, the set on the right has 0 elements, right? And this is a bizarre distinction, but that's how set theory people like to do things. And in fact, there is a way to define the integer numbers based on this bizarre observation. Let's not, fortunately, we don't need to care about it here. Okay. Now, an important operation that we want to do with string is concatenation, right? We have two string united, I don't know, space. This would be one string, and the other one would be states, right? And we might want to concatenate them together and get united states. By the way, this is pretty standard. We use this special letter to designate space, right? We will use it in a lot of cases. Okay, so again, how do you formally define concatenation? Well, you can always define it, in the natural way. You just take two sequences and you put one after the other. It's intuitively very clear. Or you can, define it more formally. So you can just say that it's, if concatenation of two string x, y is x if y is the epsilon, the empty string, and otherwise you can concatenate them by looking on x, using the definition of x, saying that it's a of w, and then concatenate. You say the concatenated string is a, and then the tail of x, which is w, concatenated to y, right? So you get a recursive definition. It's all a bit weird, but it works. Okay. Important thing about concatenation is that it's associative, right? And by that we mean that if I concatenate three strings, it doesn't matter how I put the parentheses, right? I can first concatenate x, y, and then z, or alternatively, if I prefer, I can concatenate y and z, and then concatenate x, right? So, which in particular means that it's okay when I write concatenation to just write it without parentheses, because where you put the parentheses doesn't matter. Okay. Unfortunately or fortunately, concatenation is not associative, so it's not true that you've xy for two strings is equal to yx, right? So to say that, just pick some ABA, and y would be CDC, right? So this xy is ABA CDC, while the yx, when we concatenate, is CDC ABA, right? Clearly not the same thing. Okay, so it's concatenation is not associative. Finally, if you want to think about concatenation as multiplication, then the identity element, the one in this multiplication, is the empty string, right? Epsilon, because if you concatenate epsilon to any string, you still get the same string. Okay, now a substring, right? Let's take an example. Sariel. So a substring it's a sequence, so it's just a sub-sequence, a consecutive subsequence, right? In particular, epsilon is always a substring of a string because it's a sequence of length 0. you can find it anywhere you want, either in the beginning of the string or between characters or in the end. Epsilon is, hiding everywhere. So this would be a substring. A prefix, of course, is the initial part of a string, right? You just take a substring, which is the beginning of the string. This is a prefix. And similarly, a suffix is the last few characters. And I promise in the future not to use my name as an example. Okay. And you can define it formally if you want, but let's not do that. Maybe I should say, by the way, that the formal definition of, maybe let me define the formal definition. The formal definition of a substring is that you have a string, you can write it as a concatenation of 3 string x, y, z, and then whatever y is, it's a substring. Right, so that's one way of thinking about substrings. Okay, one thing that is going to be extremely useful is to concatenate a string with itself several times, and we're going to use this a power notation for that. So blah to the power 4 is just the string blah, 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 which I'm sure a lot of you are feeling just about now like that, seeing all this stuff. Okay, another useful thing that we're going to do quite a bit is concatenation of sets, right? So we have 2 sets that have strings in them, and then we concatenate the set, which means that we are essentially concatenating string where the first one is from the first set and the second one is from the second set in a natural fashion. So, here's an example. I have x and y, which is a string, right? So if I take, if I take the first string to be Rover and the second string to be Fluffy, then the concatenation is going to be Rover Fluffy, and indeed, this is this string in this concatenated set, and the size of the concatenated set is of course going to be the product of the sizes of the 2 original sets, assuming of course, assuming nothing. Well, you have to be more careful about it, right? So it's not quite the product, but intuitively you can think about this as the product. Of course, one can come up with examples where it isn't. Okay, let's go back to sigma star. So sigma star, as I said, is a set of all possible strings, and you can define it as the union of sigma n over all strings of length n. Right, so you can define it as follows. Now, there is a special case that you should, remotely care about, which is what about sigma 0, right? And sigma 0 is just going to be the empty string, right? Because that's kind of the only string you can get without, well, it's going to be the set of empty strings. Right. Okay, and that's it, right? And sigma n, to remind you, is again all string of length n, right? We treat sigma as a collection of string of length 1, right? 1 character, and then we raise it to the power n, so we get all string of length n. Okay, there's going to be this thing about sigma plus, which is going to be all strings that, all finite strings that you can generate using the alphabet sigma, but I'm not allowing you the empty string. And, this is going to be just convenient to deal with it later. Okay, now we're going to use throughout the course this word language, which is just a fancy word of saying a set of strings, right? So think literally on a language as, I give you a dictionary of a language, I don't know, Spanish, and I just write down all the words in the dictionary, and that could be the language, right? Now, this is of course an abuse of the word language, but that's the meaning we are going to use it throughout this course. Okay, so here's an exercise to review all the things that I talked about go over all those questions and verify that you know how to answer them correctly. And that's it.